Welcome to our last break-free Lunch and Learn webinar series of the year. I'm your host, Laura with Videri Creative. So for anyone new to Wavelogix, here's some background info. Founded in 2021, Wavelogix partnered with the Indiana Department of Transportation and Purdue University to enhance road and bridge reliability while minimizing traffic disruptions. Our patented Rebel concrete strength sensing system offers real-time in-place concrete measurements, streamlining project schedules and reducing costs. Our speaker, Joe Turek, is a seasoned engineer with a BSCE from Notre Dame and an MBA from Northwestern. He holds 5 patents in microwave telecommunications technology and is a registered professional engineer. Now, for anybody new that just joined us, if you have questions during the webinar, you can use the Q&A function below and we will answer your questions at the end. Now I'll hand it over to our presenter, Joe Turek.
Thanks, Laura. Appreciate that. Good afternoon, everyone, or morning, depending on where you are on the planet. Today's webinar, our final one in the series, as Laura had mentioned, is all about how to eliminate cylinder breaks. That's our motto is break free, and our sensors are something that give us the ability to minimize the use of cylinder breaks or flexible beam breaks. And why is strength really important and critical in pouring concrete? Let's just go over that so that we have a basis and a framework to understanding strength in concrete. You know, in horizontal work, it's removing your forms around the concrete. Knowing exactly when to move them is critical. If you remove them too soon, concrete would slump and fall out of its mold. Removing scaffolding, very important if you're building multiple floors and you have scaffolding holding up that floor. You want to make sure that the concrete is hard enough before you move that. Post-tensioning, very important in bridges and parking decks, where you actually pull cables to put stress on the concrete in tensioning. And if the concrete hasn't cured enough, concrete's going to crack prematurely. So it's important to be at a particular strength before you do that. Releasing traffic, you want to make sure that you're not letting heavy equipment roll over your newly poured pavement, that it's reached a particular strength. Segment pouring, if you're pouring columns or walls, you usually pour those in segments. Let the lower section cure before you pour the next portion of it. And again, if it's not cured enough, it's going to slump or fall apart or crack. Panel lifting and tilt-up operations. You may have seen this along warehouses that are going up and a lot of structural buildings that use walls that are pre-formed. Those get lifted up and put in place. And again, if they don't reach the proper strength, they'll fall apart and crack. That's a problem. And a lot of times final payment is very important to meet your final strength. You get paid on that final strength. And knowing when you hit that strength is important to make sure that you get paid. And what happens if we don't get the strength right? Things will go wrong. Buildings will collapse, bridges will collapse. Those are things that we don't want to have happen. So knowing that strength is incredibly critical in our industry. So I like to title it Breaking Bad. For 100 years, we've been using brake technology, essentially, to determine the strength of the concrete. We pour a companion cylinder or flex beam at the time that we pour the structure, and then we crush it. It's time consuming, it's prone to failure, and it's not real time. It's also very inefficient and costly. It requires skilled labor, which is getting more difficult to find. Usually the cost is somewhere between $800 and $1,300 to do cylinder breaks, and delays in getting it wrong could cause scheduling problems. You know, there are a lot of hopes we have with cylinder breaks, but the reality is that it's not real time and we're not getting accurate strength. Those are things that we're looking for in today's mixed designs. We need cost-effective and reliable solutions, and cylinder breaks just don't provide those timely and useful insights. More specifically, the disadvantages of using cylinder breaks, which is very common with destructive testing, is they're heavily reliant on proper sample preparation. And we require to use skilled labor in following those procedures. For those of you who don't know the process in making a cylinder, typically at the end of the truck that's delivering the concrete, when they're dumping out the concrete to be used in the operation, a test technician would take a sample of that, usually in a wheelbarrow of the concrete, and then they would fill up cylinders. Those cylinders are usually 6 inches in diameter, 12 inches high, or more popular, 4 inches in diameter and 8 inches high. You fill that cylinder up halfway with cement, then you use a rod and you tap it down 25 times, and then you use a mallet and you pound it around the outside of it 5 times. Then you fill it again, pour it, you rod it again, you pound it, and then that's one cylinder. And you do that 15 times. It's a pretty laborious process. And you can imagine that after a while, you get tired of not rodding enough or not pounding it properly. And if you don't follow that procedure, there's a potential that that cylinder is made wrong. And if it's made wrong, it's not going to give you accurate compressive strength when you go to crush it. On top of that, that cylinder typically has to stay at the site for about 24 hours until it gets hard enough to transport it. If you transport it before it's hardened properly, the jiggling around and bouncing around in a transport vehicle, your car off of a job site or truck, that could cause problems in the cylinder not coming up to full spec. And then once you get the samples demolded and brought to the lab, they typically have to be kept wet and wet right up to the moment of testing to avoid inaccuracies. And a lot of people take the samples, they store them in a water bath environment at a constant temperature of 70 degrees. And then they take them out, they might dry them off, and then they might crush them later, but they're supposed to continue to stay wet. So there's a lot of ways that technicians don't necessarily follow all the process procedures that are required by the specifications. And in doing so, you end up with inaccurate results. Also today, we have many, many different new mix designs coming on board on ways to reduce the amount of carbon impact by reducing the amount of cement and adding in other additives. And those new mixes are finding that it's much more difficult to make accurate cylinders. Also, the aggregate composition significantly influences the way the cylinder is made and other variability. And aggregates can be anywhere from under an inch to as great as 3 inches in size. And so if you have large aggregates and you put it in the wrong type of compressive mold, you could have inaccuracies. So a lot of things can go wrong in making cylinders, and yet we use that in our operation every day to measure the strength. A study was done in California, which I find really very interesting. It shows this study on the graph shows the age of the concrete and the compressive strength of cylinders that were made. Each one of the blue dots is a cylinder that was crushed. The red line is the actual strength of the concrete at that point in time and showing its appropriate strength. Now, what's interesting is that California had 200 independent test technicians make cylinders from the same concrete mix over a period of months and then submit them for crushing, and then they recorded that. And the very interesting thing is that that those blue dots are all over the map. There's almost a 500% error associated with some of those. And this is, again, what we're using every day to measure the strength of our concrete. So not the best process. It ends up, one of the things that happens when you're not really certain if your cylinder is right or going to give you the right data. But you need to keep your production schedule moving, and you need to be able to get paid, and you got to make sure that you hit the required strength. The industry over cements the concrete by almost as much as 25%. So they're adding more cement in to make sure that they get to the hardness they need, because they know that the cylinders may give them inaccurate results. And so what happens? It results in higher costs because cement is the expensive part of concrete. It creates a higher carbon footprint because it's the cement that's giving us a higher carbon footprint in the concrete. And the reality is, by adding more cement, you may be making it stronger in compressive strength, but it actually makes it a weaker structure because concrete has very poor performance in flexural. So side by side, it's very weak. Compressive, it's very strong. You can make it stronger, but you make it weaker this way. So if you have an outdoor concrete that is experiencing freeze and thaw many times, that freezing and thawing, expanding contraction makes the concrete actually weaker. So all of these things are necessarily a result of the methodology that we used to do to measure the strength of concrete. Compare that now to our Rebel sensor. And our Rebel sensor is a real-time sensor that's buried in the concrete. Normal cylinder breaks are broken on a periodic schedule per specification that's done at 1 day, 3 days, 7 days, 14, and 28 days. 1 and 3 days give you early strength determination to allow you to do some of the next operations. 14 and 7, 14, and 28 days give you kind of final strength or an area where you would get paid on. But it's not real time. And if when you go to crush your cylinder, you don't come up to the specification or the strength that you need, you now have to wait. If you did it on 1 day, you're going to have to wait to 3 days. If you do it at 3 days, you're going to have to wait to 7 days. And those missed days end up creating the inefficiencies in your schedule. In giving us real-time data, we also have the ability in our sensors to set alerts to notify you when you've gotten to the strength. So overall, we eliminate the waiting period. We can be saving a day or more in terms of testing and schedules. In large scale projects, you can be reducing time by a month or more, which is very significant in cost. So you lower the cost and potential for completing projects on time and even getting an early completion bonus. So how does the Rebel system actually work? We use a piezo sensor that creates a sonic wave. When the sensor is buried in the concrete, that wave is activated, and we're looking at the pressure of that wave being pushed into the concrete. We measure that pressure through measuring the resistance or the impedance of that wave. What's interesting is that as you look at the pressure of that wave, we vary the frequency of that wave from 0 to 200,000 cycles per second. And when you hit a point called resonance frequency, or the resonance of the material, and every solid material, based on its stiffness, will have a resonant frequency. You can see the chart on the right actually is measuring the different frequencies at a different resistance level. When you hit its lowest point of resistance, you peak, and that peak is the resonant frequency. On the left-hand side of the chart, you can actually see the wave representation of that wave. When it actually hits at resonant frequency, it kind of explodes. And that's what we're looking for. Now, what's so exciting about resonant frequency of a material is that it's equal to the modulus of the material. And the modulus of the material in civil engineering is what determines the compressive strength. So if we know the resonant frequency, we'll know the modulus. If we know the modulus, we'll be able to know the compressive or flexural strength of that material. And if we look at that at concrete as it's curing and as it gets stiffer, and we look at that resonant frequency, we're going to see it shift from the left to the right. And you can see in the graph the corresponding compressive strength, 120 psi, 500, 1100, 2000 psi. We have a very unique way using a non-destructive test in real time that gives us accurate compressive strength as that concrete cures. And that, in essence, is the basis of our product and how it works. The sensors are very easy to deploy. You can either put them on the ground if you're doing pavement and roll the concrete over it, or you can tie it to rebar. So it's simple to deploy. Cable comes out from the sensor, and that plugs into a data logger. So the sensor itself is relatively flat, half an inch thick, about 4 inches in diameter. It has a piezo wave generator in it, and we throw a temperature probe in. So we're measuring both the temperature of the concrete and we're measuring the strength and looking for the resonant frequency. The data logger that the sensor plugs into is what powers the sensor. It has its impedance meter inside of it. It has a GPS location chip, so we know exactly where the sensor is located. It has a cellular radio, so as soon as we plug the sensor into the data logger, it connects up to the cellular network and can start sending data to our database in the cloud. It's powered by a lithium-ion battery that has a 28-day capacity. The unit is completely sealed, and we use wireless recharging, so there's no plugging into the device to charge it. It comes with a very nice little cradle for dropping the sensor in to plug the cradle into the wall or into an outlet or into your computer. And it's a very durable housing that can withstand environmental pressures. It can be powered underwater. It's completely sealed. It can withstand dropping and some of the punishments on the website. Excuse me, on the work site. Graphically, how this works, you have each one of the data loggers, which needs to be plugged in for at least 3 days to the sensor. As it's gathering critical data, it's sending information every 15 minutes up to the cloud. Our machine learning algorithm works on that data to create and generate the compressive strength. It then reports that down to our dashboard, and that dashboard then could be viewed on either your computer, your phone, or your tablet, anywhere that you have internet connection. A little closer look at what our dashboard does is it will give you compressive strength in real time, hour by hour, and show you what the strength is. You can set points to send text alarms when you reach a particular strength. And then at the same time, we're giving the temperature of both. The red line shows the in-place temperature at the sensor, so in the concrete. And then we have another temperature probe in the data logger, so we're giving the outside ambient temperature of the environment. And you see both of those two at the same time. So very, very powerful information, just about everything that you need to know about your concrete as it's curing, both the temperature of the concrete and the strength, all in real time. So just as a reiteration, we have an embedded sensor, gives us real-time information, uses a machine learning algorithm to estimate the strength. We have a AASHTO certification T412 that was just released in July. So that's been approved by all the DOTs in every state across the country. We, on top of real-time data, we believe we can accelerate construction schedules. We can reduce the construction labor cost. We potentially can reduce cement usage by 20%, becoming more carbon friendly. We definitely believe we can eliminate the use of cylinder brakes or flexible beam brakes. And we think that we have a good start on helping people reach a more healthy environment by reducing the carbon footprint. And that concludes our webinar for today. Hopefully that's a little more information than you might have had before. And at this time, I'm happy to take some questions and go from there.
Okay, great. Thank you so much, Joe. If anybody has a question, you can put it in the Q&A tab below. We do have one question coming in here. When was the sensor invented?
The sensor was invented back in 2017. We took a couple years to validate the technology. Then we started prototyping it. In 2023, we came up with our first version that we took out and did field trials across the country for the whole year. And then this year in 2024, we released a production version, and we've been selling it out into the field. We have over 1,000 sensors that have been deployed. We have over 60 customers who are using it successfully on all sorts of projects: bridges, paving, patchwork, ready mix, uh, mixes, and vertical construction programs.
Okay, great. Next question is the Rebel sensor reusable?
The Rebel sensor itself is a one-time use. You bury it in concrete, so you're not getting it back. It has a 16-foot cable that comes out of the sensor. That cable length could be extended up to 100 feet. It plugs into the data logger. The data logger is what's reusable for sensor on sensor and sensor. So we expect long life out of the data logger and one-time use out of the sensor.
All right, next question is what has been your biggest challenge in getting people to accept this new technology in the industry? Has there been any hesitations with it, etc.?
Um, this is the concrete industry is a very old industry, very resistant to change. But many people are looking at new technologies and adopting it. So we see both people who are resistant to change and those that are excited about trying out new things. Um, but with any new technology, it's one is making people aware that it exists. Number one. Number two is uh, explaining it to people so they understand it and are then willing to use it, getting a quote to know what it costs, and then from the quote stage to actually buy the product, and then to find a project to deploy it in, and then to validate that it works. And typical validation is, unfortunately, you match it against the cylinder breaks because that's what we use today. And then once the customer gets comfortable that our sensor is giving real accurate data compared to cylinder breaks, and they see the value of having real-time accurate data and the ability to eliminate cylinder breaks, then it becomes more adopted and used on the next project. We've really only been marketing into the industry for this year, and we're getting a lot of traction, and we're pleased with the results that folks who have tried it are continuing to use it. And I think it's a snowball effect. You start using it, people start to talk about it, and then we get more people who are interested in it, and away we go. But it's going to take some time.
Of course, thank you. Can the sensor be used on mixed designs with fibers, especially steel fibers? How much does setting the target strength on a particular sensor affect the strength data?
So we've used the sensor in all different types of mixes, all types of fibers, metal fibers, plastic fibers, fiberglass fibers, anything that people have been mixing in with fibers. Rebar does not affect the sensor readings. Um, Other types of SEMs, non-semacious materials or other semacious materials that are put into the mix to reduce the amount of concrete, all we've tried them all. And all of those additives tend to affect the strength one way or the other. And the cool thing about our technology is we're measuring that strength. We're not dependent on temperature. We're not dependent on moisture. We are dependent on the actual strength of the material. And so whatever you add into it typically does not affect our sensor readings. And Laura, I wasn't certain of the second half of that question. Could you repeat that again?
Yes, of course. How much does setting the target strength on a particular sensor affect the strength data?
Well, I'm not certain that of what the question really is. If you set if you set the target, and is that meant to be? I'm not certain if that's in our dashboard. If we're setting a setting, it doesn't affect it. if you're setting a target, you have a target that you have to meet. The sensor is really independent of any type of targets. It's just giving you what your data is, what the strength is at that point. When you hit a particular target, you can set a notice to tell me I've hit it, and it won't tell you that you've hit it until you've actually gotten to that stage. So I apologize if I haven't really answered that question properly because I'm not really certain what the question is, but that's the best I can give you.
Thank you. Yes. Sorry if I butchered this name, but Carthian, let us know if that answers your question. If not, please ask a follow-up. That was perfect. Okay, great. Thank you. Okay. Yeah, thanks, Joe. Next question. How much of your competitors have also developed this break-free technology or are on their way to bringing the same technology to the market?
So our competitive landscape right now has just been maturity sensors. And maturity sensors to date do nothing more than just measure the temperature of the concrete. And then do a correlation between the temperature and what the compressive strength is at a particular time. The downside of maturity sensors is that temperature only lasts for about 20 hours before the concrete starts cooling off. And so anything after 20 hours is really more or less a calculated risk in terms of what the true strength might be. It's also affected by moisture. It doesn't determine too much moisture, too little moisture in those calculations. It has to be calibrated for every mix design, where our device does not require calibration at all. You can change the mix. You don't have to recalibrate our sensors. They're calibration free, which makes it unique, and we're not dependent on temperature. Now, there is one of our competitors, a good competitor in the marketplace, probably the largest that makes maturity sensors is Geotech. And there's several others that make maturity sensors. Geotech has developed a device similar to ours. They do not use the piezo technology, but they are using technology different than temperature, and so that's good. So I think competitors are now starting to see maybe the failings of maturity sensors, and I think they're trying to address that issue with coming up with something, another non-destructive test that's similar to what we're doing. We believe we're the market leaders in this type of technology, looking at the resonant frequency and working with the modulus and compressive strength. And we encourage other competitors to try and do the same because we think it's a much better technology than both compressive cylinders and maturity sensors.
All right, and we have one more question. What information about the mixture is required to use the cloud machine learning algorithm?
We have, when you deploy the sensor, you log the sensor into our dashboard so that our algorithm knows where to take the data and where to put it so that it gets to the right program, the right mix design. We actually ask our customers to give us a description of the mix design, telling us if it's what its makeup is of amount of cement, amount of water, amount of aggregate, amount of sand, and if there's any other SEM additives into it. That gives us a better idea of how to set the model up. What we're really trying to determine is fast curing concrete from slow curing concrete to ultra high strength concrete to slower concrete in the mix designs. And that just helps the model be more accurate. We don't actually use the specifics of the mix design to drive our model, but it does help for the model to know what type of animal it's dealing with basically in concrete. So that is kind of a requirement to put the basis of the mix design into the dashboard when they're setting up the sensors.
All right, that is all the questions we have. Thank you so much, Joe, and thank you everybody for joining us today. Again, if you want to learn more, you can go ahead and scan the QR code on the screen. And thank you so much.